Here's something that kept me up last night. We're all obsessed with which AI model is smarter, which company released the latest breakthrough, who's winning the race to artificial general intelligence. But while we're watching that shiny object, there's a completely different crisis brewing underneath everything. And it's not about algorithms or data or even compute power in the way most people think about it. It's about something far more fundamental, far more physical, and honestly, far more expensive to fix. Think about it this way. Right now, today, there are AI data centers being planned that will consume more electricity than entire countries. Not cities, countries, and we're not talking about some distant future scenario. These facilities are being designed and built right now. The problem is, our electrical grids weren't built for this. Our cooling systems weren't designed for this. Our entire physical infrastructure for computation is based on assumptions from a world where the most power-hungry thing in a data center was maybe some Bitcoin mining operation or a really busy search engine. We've entered a completely different universe, and almost nobody is talking about the infrastructure crisis that's coming. So today, we're going to go deep on something that rarely gets discussed outside of very technical engineering circles. We're going to explore the physical constraints, the engineering challenges, and the systemic bottlenecks that are quietly becoming the limiting factor in AI development. Not model architecture, not training techniques, but watts, thermals, water supply, and electrical grid capacity. And here's why this matters to you even if you're not an engineer. These physical constraints are going to determine which companies survive, which countries dominate AI, and ultimately, how AI gets deployed in your life. The software might be ready, but the hardware infrastructure decidedly is not. Let me start with a story that illustrates just how severe this problem has become. Last year, a major tech company tried to build a new AI training facility in a region that seemed perfect on paper. Good tax incentives, available land, supportive local government. They got 6 months into the planning process before they hit a wall. Not a regulatory wall, not a financial wall, but a literal electrical capacity wall. The local grid couldn't provide the power they needed. Not without a multi-year, multi-billion-dollar upgrade to substations, transmission lines, and generating capacity. The project didn't just get delayed. It got cancelled and relocated. This wasn't some edge case. This is becoming the norm. And here's what makes this even more interesting. The power requirement isn't the only constraint. These facilities need massive amounts of water for cooling. They need fiber optic connectivity that can handle unprecedented data throughput. They need physical space with specific geological characteristics because the weight of the equipment and the vibration from cooling systems creates structural engineering challenges. We're not just building data centers anymore. We're building what are essentially industrial power plants that happen to run computers. The scale has shifted so dramatically that the entire discipline of data center design has had to be reinvented in the last 3 years. Now, let's dig into the power problem specifically, because this is where things get really fascinating and a bit alarming. A modern AI training cluster running something like GPT-scale models can draw 50 to 100 megawatts. For context, that's enough to power about 75,000 homes. One facility. And we're not talking about peak usage during some special event. That's baseline, continuous load. These systems run 24/7 for months during training runs. The electrical demand is constant and enormous. And here's the kicker. The projections suggest that by the end of this decade, AI data centers globally could consume as much electricity as entire major industrialized nations consume today for everything. This creates some really thorny problems that go way beyond just building more power plants. First, there's the grid interconnection issue. Most electrical grids were designed for relatively predictable, distributed loads. Residential areas draw more power in evenings and mornings. Industrial areas draw power during business hours. The grid was built with these patterns in mind, with capacity to handle peaks and valleys. But AI data centers represent what engineers call a baseload anchor tenant. They draw massive, constant power with almost no variation. Plugging one of these facilities into an existing grid is like trying to add a major city to infrastructure designed for suburbs. It doesn't just strain the system. It can destabilize it. Then there's the generation question. Where does this power actually come from? In many cases, especially in the United States, It means bringing old fossil fuel plants back online or building new ones, which creates obvious tension with climate goals. Some companies are pursuing dedicated nuclear power agreements, which sounds great until you realize that building new nuclear capacity takes a decade or more and costs billions. Others are looking at renewable sources, but solar and wind create their own challenges because AI training can't pause when the sun isn't shining. You need either massive battery storage, which introduces new cost and material constraints, or you need fossil fuel backup, which defeats the purpose. There's no easy answer here, and the decisions being made right now will have consequences for decades. Let's shift to cooling, because this is where the engineering gets really creative and really desperate. Traditional data centers used air cooling. Banks of servers with fans pushing air through, with the hot exhaust managed through careful airflow design. That worked fine when individual chips dissipated maybe a couple hundred watts. Modern AI accelerators can dissipate 600, 800, even 1,000 watts per chip. And you might have thousands of these chips in one facility. Air cooling simply cannot handle that heat density. The physics don't work. So the industry has pivoted to liquid cooling, which is way more efficient at thermal transfer but also way more complex. We're seeing everything from direct-to-chip liquid cooling systems where coolant flows through cold plates mounted directly on processors, to full immersion cooling where entire server boards are submerged in non-conductive coolant fluid. These aren't incremental improvements on existing designs. These are completely different engineering paradigms. And each approach creates new challenges. Liquid cooling means you need pumps, heat exchangers, coolant distribution infrastructure. You need monitoring systems to detect leaks. You need redundancy because a cooling system failure in a high-density AI cluster can destroy millions of dollars of hardware in minutes. The chips will literally thermal throttle and shut down to protect themselves, taking your multi-month training run with them. But here's where it gets even more interesting. Some companies are going beyond just managing heat to actually reusing it. There are projects where data center waste heat is being routed to district heating systems for nearby communities. The hot water coming out of the cooling loops, instead of being dumped into cooling towers or rivers, gets piped to residential and commercial buildings for heating. It's an elegant solution that addresses both the cooling challenge and the broader energy efficiency question. But it only works if your data center is located near communities that need heat, which adds another constraint to site selection. You can't just build in the middle of nowhere anymore. Geography, climate, proximity to population centers, all of this suddenly matters in ways it never did before. Speaking of site selection, this has become its own specialized discipline that barely existed 5 years ago. Companies are now evaluating potential data center locations based on a matrix of factors that reads like something from a city planning textbook. Electrical grid capacity and upgrade potential. Water availability and rights, because cooling consumes enormous amounts of water. Climate considerations, since ambient temperature affects cooling efficiency. Proximity to fiber optic backbone infrastructure. Geological stability and load-bearing capacity of the land. Local regulations and environmental permitting. Community relations and political support. Tax incentives and economic development agreements. And increasingly, climate risk assessment because building a billion-dollar facility in a region prone to extreme weather events or water scarcity is asking for trouble. This is creating some really interesting geographic shifts in where AI infrastructure gets built. Regions with abundant hydroelectric power, like the Pacific Northwest or Quebec, are seeing massive investment. Northern climates where cold ambient temperatures reduce cooling loads are suddenly prime real estate. Countries with surplus energy generation capacity and favorable policies are positioning themselves as AI infrastructure hubs. We're watching a new industrial geography emerge in real time, and the implications go far beyond just where servers live. This is about economic development, job creation, and strategic national advantage in the AI era. Now let's talk about something that doesn't get nearly enough attention: the supply chain constraints for AI hardware. Everyone focuses on chip design and manufacturing, which are absolutely critical. But there are bottlenecks throughout the entire stack that are less visible but equally important. High bandwidth memory, which is essential for AI accelerators, comes from only a handful of manufacturers globally. Advanced packaging technologies that allow chiplets to communicate at high speeds are capacity constrained. Power delivery systems that can supply hundreds of amps to individual processors require specialized components. Optical interconnects for data center networking are in high demand. Every one of these components has lead times measured in months or years, and every one represents a potential choke point. The advanced packaging piece is particularly fascinating because it represents a fundamental shift in how we build computational systems. For decades, the semiconductor industry focused on making individual chips faster through process node improvements. Smaller transistors, higher clock speeds, more cores on a single die. But we've hit physical limits. You can't just keep making transistors smaller indefinitely. The laws of physics eventually say no. So the industry has pivoted to advanced packaging, where you take multiple smaller chiplets and connect them so tightly that they act like one large chip. The connections between chiplets need to be incredibly fast and incredibly dense, which requires new materials, new manufacturing processes, and entirely new design methodologies. This is where things like silicon interposers, through silicon vias, and hybrid bonding come in. These are techniques that allow multiple dies to be stacked vertically or arranged side by side with connections that have bandwidth measured in terabytes per second. It's an engineering marvel, but it's also incredibly difficult to manufacture at scale. Yields are a constant challenge. Any defect in any of the chiplets or in the packaging process itself can destroy the entire assembly. And because these are cutting-edge processes, there are only a few companies in the world that can do it, and they're completely maxed out on capacity. If you want advanced packaged chips for your AI system, you're getting in line behind everyone else, and that line is long. Let's dig into memory specifically, because this is another critical bottleneck that determines AI system performance. AI models, especially large language models and computer vision systems, are incredibly memory-intensive. They need to access huge amounts of data very quickly during both training and inference. Traditional memory architectures can't keep up. The gap between compute speed and memory bandwidth has been growing for years, and AI has made that gap a critical problem. High bandwidth memory, or HBM, solves this by stacking memory chips vertically and connecting them directly to the processor, giving massively higher bandwidth than conventional memory. But HBM is difficult to manufacture. You're stacking multiple memory dies using through silicon vias, which are tiny vertical conductors that go through the silicon itself. Any misalignment or defect can kill the whole stack. Thermal management is tricky because you're packing a lot of heat-generating memory into a small volume. And testing is complex because you need to verify that every die in the stack works perfectly and that all the interconnections are good. Manufacturing yields have improved dramatically over the last few years, but it's still a challenging process, and demand far exceeds supply. Every major AI chip designer needs HBM, and there aren't enough fabs producing it to meet demand. This creates some interesting strategic dynamics. Companies that can secure HBM supply have a competitive advantage. Those that can't find themselves limited in what they can build. Some companies have responded by developing their own memory solutions or forming exclusive partnerships with memory manufacturers. Others are exploring alternative architectures that are less memory intensive, though that often means sacrificing performance. The memory bottleneck is shaping AI system design in fundamental ways, and it's not getting solved quickly because building new HBM manufacturing capacity takes billions of dollars and years of time. Now, let's talk about a constraint that's becoming increasingly important: sustainability and environmental impact. AI's energy and water consumption are starting to draw serious scrutiny from regulators, environmental groups, and the public. We're seeing the beginning of what could become a significant social and political backlash if the industry doesn't get ahead of these concerns. The environmental footprint of AI is no longer an abstract future concern. It's a present-day issue that's affecting real communities and ecosystems. Take water usage as an example. Data centers use water primarily for cooling, either directly through evaporative cooling towers or indirectly as part of chiller systems. A large AI data center can consume millions of gallons of water per day. In regions facing water scarcity, this is becoming a serious point of tension. There have already been cases where local communities have opposed data center construction because of concerns about water table depletion or competition for limited water resources. Companies are responding by investing in water recycling systems, using alternative cooling methods, and being more selective about where they build. But the fundamental tension remains. AI needs cooling, cooling needs water, and water is increasingly scarce in many regions. The carbon footprint of AI is another growing concern. Even if you're using renewable energy to power your data center, which many companies claim to do, the reality is often more complicated. Renewable energy certificates let you claim carbon neutrality by buying credits equivalent to your usage, but that doesn't mean your facility is actually running on renewable electrons. In many cases, data centers are connected to grids that are predominantly fossil fuel powered, and the renewable credits are essentially accounting fictions that make the numbers look better. Some companies are taking more direct approaches, signing power purchase agreements for dedicated renewable capacity or even building their own generation. But these are expensive and complex undertakings that add years to project timelines. There's also the embodied carbon in the hardware itself. Manufacturing chips, especially advanced ones, is energy intensive. Mining and refining the rare earth elements and specialty materials used in electronics has environmental impacts. And the rapid upgrade cycles in AI hardware mean equipment becomes obsolete quickly, creating electronic waste challenges. When you add all of this up, the total carbon footprint of AI is substantial and growing. Some estimates suggest that training a single large language model can have a carbon footprint equivalent to several cars over their entire lifetimes. Multiply that across the industry, and you start to see the scale of the problem. Let's shift gears and talk about network infrastructure, because this is another often overlooked bottleneck. AI systems, especially large distributed training clusters, need to move massive amounts of data between nodes. We're talking about terabytes or even petabytes of data flowing across the network during a training run. Traditional Ethernet networking, even at high speeds, struggles with this. The latency, the packet overhead, the complexity of managing thousands of connections, it all adds up to inefficiency. The industry has responded with specialized networking technologies designed specifically for AI workloads. InfiniBand has been the go-to solution for years in high-performance computing, offering low latency and high bandwidth for tightly coupled clusters. More recently, we're seeing the emergence of optical interconnects and silicon photonics, where data is transmitted as light rather than electrical signals. This offers the potential for even higher bandwidth and lower power consumption. But it also introduces new engineering challenges. Optical components need precise alignment. Lasers need thermal management. Converting between electrical and optical signals adds complexity. And the entire ecosystem of switches, routers, and cables needs to be redesigned for optical networking. There's also the challenge of network topology and congestion management. In a large AI training cluster, every node needs to communicate with many others, creating complex traffic patterns. Traditional network architectures can create bottlenecks where certain links become saturated while others are underutilized. Companies are experimenting with new topologies, custom routing protocols, and congestion control algorithms designed specifically for AI workloads. This is another area where the old playbooks don't work, and engineers are having to innovate in real time. Now, I want to talk about something that's critically important but rarely discussed outside of very technical circles: reliability and redundancy in AI infrastructure. When you're running a training job that takes months and costs millions of dollars in compute time, any failure is catastrophic. A hardware fault, a cooling system glitch, a power fluctuation, any of these can crash your training run and force you to start over or try to recover from the last checkpoint, which can set you back days or weeks. This makes reliability engineering absolutely paramount. The challenge is that with the complexity and scale of modern AI infrastructure, failures are inevitable. You're dealing with thousands or tens of thousands of components, any one of which can fail. The approach has to be designing systems that can tolerate failures gracefully. Redundant power supplies, hot swappable components, checkpoint systems that save model state frequently so you can recover quickly, sophisticated monitoring that detects issues before they cause cascades. Every layer of the stack needs resilience engineering, and that adds cost and complexity to systems that are already expensive and complex. There's also the human element. Operating these massive AI facilities requires specialized skills that are in short supply. You need people who understand high-performance computing, power systems, cooling engineering, network architecture, and AI workload characteristics. That's a rare combination of expertise. Companies are investing heavily in training programs and competing aggressively for talent. The people who can design, build, and operate these facilities are becoming as valuable as the AI researchers themselves. Infrastructure expertise is becoming a strategic differentiator. Let me bring this back to a bigger picture question. What do all these infrastructure constraints mean for the future of AI development? In the near term, they're going to create winners and losers based on who can secure the necessary physical resources. Companies and countries with access to power, cooling capacity, manufacturing, and supply chains will have an advantage. Those without will be at a disadvantage regardless of how good their algorithms are. We're seeing this play out already with some organizations struggling to get access to the compute they need while others with better infrastructure positioning are racing ahead. Medium term, these constraints are going to drive innovation in AI efficiency. If you can't just throw more compute at the problem because the infrastructure won't support it, you have to get smarter about how you use the compute you have. We're already seeing this with techniques like model compression, quantization, efficient architectures, and training algorithms that require less computation. The infrastructure crisis is forcing the field to optimize in ways it might not have otherwise. That's actually a positive development because it means AI could become more accessible and deployable rather than requiring ever larger data centers. Longer term, I think we're going to see a fundamental re-architecting of how AI computation gets done. The current paradigm of massive centralized training facilities might give way to more distributed approaches. Federated learning, where models are trained across many smaller sites. Edge computation, where AI runs directly on devices rather than in the cloud. Specialized regional AI infrastructure optimized for specific climates and resources. The constraints aren't going away, so the systems have to adapt to work within them. There's also a geopolitical dimension to all of this that's increasingly important. AI infrastructure is becoming strategic national infrastructure, similar to how semiconductor manufacturing is viewed. Countries are investing in domestic AI compute capacity, securing supply chains, and developing policies to ensure they're not dependent on others for AI capability. We're seeing export controls on advanced chips, restrictions on cross-border data flows, and national initiatives to build AI supercomputers. The infrastructure layer of AI is becoming intertwined with national security and economic competitiveness in ways that will shape international relations for decades. So where does this leave us? The fundamental insight is that AI development is increasingly constrained not by what we can imagine or what algorithms we can write, but by the physical infrastructure we can build and power and cool. The limits are watts, thermals, water, rare materials, and manufacturing capacity. These are engineering problems, but they're also economic problems, environmental problems, and political problems. Solving them requires coordination across industries, massive capital investment, and long time horizons. For anyone watching this who's involved in AI, whether you're a researcher, a developer, a business leader, or a policymaker, the message is clear: infrastructure matters. The software might be ready for the future, but the hardware infrastructure is struggling to keep up. The decisions being made right now about power systems, cooling technologies, site selection, supply chains, and environmental impact will determine what's possible with AI for the next decade. This isn't sexy work that gets headlines, but it's absolutely foundational. The AI revolution isn't just about algorithms. It's about the invisible physical infrastructure that makes those algorithms run. And right now, that infrastructure is being built, strained, and reinvented in real time. The outcome of that process will determine whose vision for AI becomes reality.